Click the bell icon to get latest videos from Ekeeda.
Hello friends, in the previous lecture we have discussed about the various molecular orbital diagrams of various molecules, and now we are going to talk about how can we represent the molecular orbital diagram for the beryllium molecule. So let us talk about it. Hello friends, now we are going to discuss about how can we represent the molecular orbital diagram for the beryllium molecule. So now let us start with that one. So with the reference of the previous lecture that we have gone through, that what is the thing that we have to do over here, that is the first thing that we have to do is we have to represent the electronic configuration of beryllium. And for beryllium, that we know that beryllium has an electronic configuration of that is 4. We could write it over here. So if we represent the electronic configuration of beryllium, then in that case we will get to know that is 1s2 and 2s2. So this is the electronic configuration that we have got over here. And talking about the next thing, that is it consists of 2 shells. That is, one is the first shell and the second is the second shell, and each of it consists of only one orbital, that is s orbital, and this s subshell that is consisting of s orbital. And if we draw in the perspective of that is orbital, atomic orbital, so it consists of one orbital only, which consists of basically 2 electrons in it. So that's it. So this is the beryllium atom that we have. But since we are talking about beryllium molecule, means we have to introduce another beryllium also. And let me give it that this is beryllium A. So now we are going to compare that with of beryllium B, and we'll combine the both of two, and let us see that how the molecule will form or not. That is what we are going to study in this case. So now let us represent the energy diagram of the molecular orbitals. So let us do that. So before going with the molecular orbitals, the first thing that we have to do is we have to represent the energy level for the atomic orbital, and that is what we are going to do. So this is what I am representing, the energy level. And since the total number of orbitals or the total number of shells that are being involved in this case is basically, if you could see, that is 1s along with that of 2s. So the 1s will have a lower energy, so therefore I could write it here as, or I could represent it over here in this way. That is, it represents the 1s orbital. While talking about the 2s orbital, the 2s orbital will have higher energy, and that is what I am representing over here. And since it is an s orbital, so therefore the total number of orbital that we could say is basically it is 1. So I will represent here as 1 orbital, and here also 1 orbital. So this is what I have represented, that is atomic orbital of that is beryllium, that is Be. So the only thing that is been left out is to fulfill the electrons. So let us fulfill the electrons. So the 1s consists of 2 electrons, while the 2s also consists of basically 2 electrons. So similarly, I can make the another atomic orbital of beryllium also. So it will be very much similar to this one. We'll have the same energy level. So this is what I am representing for 1s orbital. For that is, this is the atomic orbital of beryllium 2, like of. Suppose if this is of A and this is of B, if I am representing, and again it will have a 2s orbital that is represented over here. So it consists of 1 orbital, that is what I am representing here, and here also it is the same, suppose. And the only thing that we have to do is we have to fulfill the electrons. So therefore this is 2 electrons that are being fulfilled over here and 2 electrons that are being fulfilled over here according to the electronic configuration, as well as according to the Ampere's principle and as Hund's multiplicity. So this is what we have got, and we have represented for atomic orbitals. So what will happen if we combine this two? So if we combine these 2 atomic orbitals, obviously molecular orbital will be formed. But talking about this one, that is this 1s and this 1s, even they will combine with each other so as to form 2 molecular orbitals, and the one of the molecular orbital will have lower energy, while the one will have the higher energy. But the thing is, they will compensate each other, and that's the reason that the bonding is not been formed with because of the 1s orbitals. So that's the reason that we could call it as non-bonding orbital. And obviously this 1s orbital is very close to that of the nucleus, and nucleus will not allow its electrons to bond with the other atom, because it is very much closely attached to that of the nucleus, and they have a strong force of attraction. But talking about the 2s orbital, the 2s orbital will be far away from that of the nucleus, and that's the reason that it can play a vital role in formation of a bond. So let us understand this. Suppose if the 2s orbital and the 2s orbital of the beryllium, if they come close to each other so as to form the respective number of molecular orbital. So the two energy level that will be created over here, that is two molecular orbitals. So one will be at the lower energy level, while the one will be at the higher energy level. So I'm representing, so therefore since there are two atomic orbitals, so one atomic orbital will be at the lower energy level, while the other one will have at the higher energy level. So this is what we can see, that the gap between the original one, that is, this was the original level, but after the formation of molecular orbital, that has been differentiated into two levels, and that is what we have represented over here. And now let us fulfill the electrons. So therefore the total number of electrons in the 2s orbital, because of the two beryllium, suppose they have combined with each other, so therefore we have basically 4 electrons with us. And how can we fill it? With the help of that is Ebers principle and Hund's multiplicity rule. And so let us fill it. So therefore there are a total number of 4 electrons, so 1, 2. So therefore 2 electrons are being filled over here. So remaining 2 can be filled over in the above level. So this is what we have represented over here. And the thing is, we have to represent that which or we have to designate the molecular orbital, and in this case I could say that this is what we could call it as sigma 2s orbital, while this one can be called as sigma star 2s orbital. So this is what we have. And so the whole thing that we have represented over in this level is basically, that is, molecular orbital of beryllium molecule, that is Be2. So this is what we have represented, or we can also say that molecular orbital of that is beryllium. So now let us understand that what would be the electronic configuration of the beryllium molecule. So I could easily say that the electronic configuration of Be2 molecule will be, because this non-bonding electron or this non-bonding molecular orbital, it consisted of the combination of the two atomic orbitals, in which the one which will have, that is sigma 1s, that is 2. The next one is sigma star 1s 2, and the later one it could be called as sigma 2s 2, and the last one is sigma star 2s 2. So this is what I am representing the electronic configuration over here, or we have designated over here. So this is what we have. And the next thing that we have to do is we have to give the bond order, and we know that the bond order can be given as, it will be nothing but it will be NB minus NA divided by 2. So now let us understand this one. So in this case, basically the total number of electrons that are present in the bonding orbital, that is, I am talking about the molecular orbital one. So it is basically 2. While talking about the anti-bonding orbital, that is again 2. So I could say that 2 minus 2 divided by 2, it makes 0. So the bond order is basically, for beryllium molecule, is basically 0. So this indicates that the bond between the two beryllium atom is 0. So there is no bond between the two beryllium atom, and that is what the bond order is. And we can say that usually the beryllium is the one that can exist in a monoatomic state. So even we can talk about that also. And so that's it. That is what I want to talk about. So this is the molecular orbital diagram of beryllium molecule, and it also gives a clear indication about the energy levels and the combination after that. So that's it. So thank you friends for watching this video. I hope you have understood this video very clearly, and you have to go to know various concepts behind this. And I hope you'll share this video with your friends, and just don't forget to subscribe to Ekeeda channel. Thank you so much.